Why Uber wouldn't exist without Instant. You pull out your phone and open Uber. Instantly, the app shows exactly where you are. A little blue dot. Your driver is 3 minutes away. Another dot moving toward you. This happens billions of times every day around the world. We take it for granted. But here's something that will blow your mind without Einstein's equations from over a century ago. That little blue dot would be miles off. Your driver would never find you. The entire system would collapse. Today, we're going to discover why getting a ride home depends on one of the strangest ideas in physics. Let's start with how GPS actually works. GPS stands for Global Positioning System. It's a network of more than 30 satellites orbiting Earth, about 20,000 kilometers above us. Each satellite carries an atomic clock, the most precise clock humans have ever built. These satellites constantly broadcast a simple message, "I am here." And the time is exactly this. Your phone receives these signals from multiple satellites. Then, it does something clever. Since radio signals travel at the speed of light, 300,000 kilometers per second, your phone can calculate how far away each satellite is by measuring how long each signal took to arrive. With signals from at least 4 satellites, your phone can pinpoint your exact location. But here's the critical part. GPS is basically a game of measuring time with insane accuracy. If the timing is off by just 1/1000th of a second, 1 nanosecond, your location could be wrong by 30 centimeters. If it's off by 1/1000th of a second, you could be several kilometers from your actual position. So when engineers were building GPS in the 1970 seconds, they ran computer simulations. They wanted to make sure everything would work perfectly, but they kept discovering something weird. If they followed normal physics, the physics of Isaac Newton that we all learn in school, the clocks on satellites would slowly drift out of sync with clocks on Earth. At first, they thought it was a calculation error, but the same result kept appearing without corrections. GPS would accumulate errors of about 10 kilometers per day. The system would be completely useless. This is where Einstein comes in. In 1905, Einstein published his theory of special relativity. One of its most shocking claims was this: when you move fast, time slows down for you. Not just appears to slow down, actually slows down. This sounds like science fiction, but it's been tested thousands of times. It's as real as gravity. GPS satellites move fast, really fast, about 14,000 kilometers per hour. That's faster than a speeding bullet. At that speed, Einstein's equations show that time on the satellites runs slightly slower than time on Earth. The effect is tiny, about 7 microseconds slower per day. But remember, GPS needs nanosecond precision. This tiny difference would destroy the system. Think of it like this. Imagine 2 twins. One stays on Earth. The other goes on a journey through space at nearly the speed of light. When the traveling twin returns, they've actually aged less than the twin who stayed home. They're younger. This isn't a trick or an illusion. Time literally passed more slowly for the moving twin. GPS satellites experience a tiny version of this effect every single day. But here's where things get even stranger. Just when you think you understand the problem, Einstein throws another curveball. In 1915, Einstein published his theory of general relativity. This one revealed something even more mind-bending. Gravity doesn't just pull things down. It actually warps time itself. Here on Earth's surface, we feel strong gravity. We're deep in Earth's gravitational pull. But satellites orbiting 20,000 kilometers up, they feel much less gravity. And Einstein's equations show that the stronger the gravity you experience, the slower your clock runs. Imagine space-time as a trampoline. Earth is like a bowling ball sitting in the middle, creating a big dip. You're standing deep in that dip. The satellite is up on the flatter part of the trampoline. Time runs faster for the satellite because it's experiencing weaker gravity. How much faster? About 45 microseconds per day. So now we have a paradox. Special relativity says satellite clocks should run slower because they're moving fast. General relativity says satellite clocks should run faster because they're experiencing less gravity. Which one is right? The answer: both. Both effects happen at the same time. The clocks on GPS satellites run 7 microseconds slower per day because of their speed. But they also run 45 microseconds faster per day because of the weaker gravity. When you add these together, the net effect is that satellite clocks run 38 microseconds faster per day than clocks on Earth. 38 microseconds doesn't sound like much. But remember, light travels 20 centimeters per nanosecond over a day. 38 microseconds of error would make your GPS location off by more than 10 kilometers. After a week, the system would be completely worthless. Your Uber would be sent to the wrong neighborhood. So what did engineers do? They used Einstein's equations. Before satellites are launched, their clocks are programmed to run slightly slower than clocks on Earth. Then, once they're in orbit, the relativistic effects, both from speed and from gravity, make them sync up perfectly with clocks on the ground. Every GPS signal you receive, whether from Uber, Google Maps, or any navigation app, has Einstein's mathematics built into it. His equations are running in your pocket right now. Billions of calculations per second, making sure that little blue dot shows up in exactly the right place. Think about what this means. Uber picks you up at the right address. Ambulances find emergencies in time. Airplanes navigate safely through crowded skies. Farmers plant crops with precision. Your food delivery arrives at your door instead of 3 blocks away. All of this depends on Einstein being right about the nature of time itself. This is what makes Einstein so remarkable. He didn't just figure out one thing. He revealed that reality is fundamentally different from what common sense tells us. Time isn't some absolute thing ticking away the same for everyone in the universe. Time bends, it stretches, it flows differently depending on where you are and how fast you're moving. And not only can we measure these effects, we've built entire technologies that depend on them. Every time you tap that Uber button, you're using both of Einstein's relativity theories working together. Special relativity accounts for the speed of the satellites. General relativity accounts for gravity's effect on time. Two of the most mind-bending ideas in physics, making sure you get home safely. But this raises a deeper question. If time really does slow down when you move fast, what does that actually mean? Could you travel to the future by moving fast enough? What would that feel like? And what happens if you tried to ride on a beam of light itself? In our next video, we're diving deep into special relativity. We'll explore the famous twin paradox. We'll find out why time travel to the future is actually possible and has already been done. And we'll discover what Einstein meant when he said that everything is relative. If you want to understand how time really works, subscribe and hit that bell. Because once you see what Einstein saw, you'll never look at a clock the same way again. See you in the next video.